Welcome back to the Explainer. Okay, today we are jumping straight into a seriously fascinating concept in hazardous area electrical design. We're going to be exploring intrinsic safety, or EXI. Essentially, this is a protection method where we engineer circuits to be, quite literally, too weak to ignite anything.
When we picture explosive environments like, say, an offshore drilling rig or a massive chemical plant, our very first instinct is almost always containment. We naturally imagine these massive, thick steel enclosures built to just tank a blast. But what if the absolute safest way to protect a circuit isn't some heavy metal box at all? What if instead we engineer the circuit so it is fundamentally too weak to cause an ignition in the first place? Like, even if you went out of your way to short it out on purpose? Well, that incredibly elegant approach is exactly what intrinsic safety is all about. Section 1. The intrinsic safety paradigm. Let's dive right into how this concept completely flips traditional engineering on its head. We really have two competing philosophies at play here. Over on the XD, or flame-proof side, the traditional method essentially accepts that, hey, an explosion might happen inside this equipment, so it relies on a heavy metal enclosure to cool the escaping flames and physically contain the blast. But intrinsic safety, it focuses entirely on prevention. We literally starve the spark. We keep the energy so incredibly low that ignition is physically impossible. And look, this isn't just some neat theoretical trick. Out in the real world, like on offshore FPSOs, relying on intrinsic safety means you can use much lighter cables and enclosures. That drastically reduces your weight footprint. Plus, and this is a real game changer, it allows technicians to safely perform live maintenance on instruments without even having to shut down the plant's power. To put a formal definition to it, the IEC 6007-11 standard defines intrinsic safety as a protection method that restricts the electrical energy in a circuit to levels strictly below the minimum ignition energy. Basically, every single flammable gas out there has a minimum amount of thermal or electrical energy it needs to catch fire. Intrinsic safety just mathematically guarantees that the circuit simply cannot deliver that much energy, period, under any circumstance. Moving on to Section 2, starving the spark. Using safety barriers. Let's look at how we actually achieve this strict energy limitation in practice. Because think about it, somewhere that incredibly low power sensor out in the field still has to connect back to a high power control room, and we bridge that gap using energy limiting barriers. These are the absolute heart of an XI system. These barriers, whether we're talking Zener diode barriers or galvanic isolators, are installed securely back in the non-hazardous safe area. So picture a thermocouple wire running from a highly hazardous tank. Its energy is clamped down by this barrier, acting almost like a bouncer at a club, before it ever even crosses the boundary. Even if there's a direct, catastrophic short circuit right out there in the field, the barrier ensures it just won't release enough energy to create an incentive spark. To actually pull this off, the barrier strictly regulates three specific electrical parameters. First is UO, which is the maximum output voltage under an open circuit. Then there's IO, the maximum output current that can possibly be drawn, and finally PO, the maximum output power. By aggressively capping these three values, the barrier guarantees that absolutely no dangerous electrical spark or even a dangerous thermal hotspot can form out there in the hazardous area. Section 3, fault tolerance categories. Now, a really crucial point to understand here is that not all intrinsically safe circuits offer the exact same level of protection. We always have to match the level of protection to the actual level of risk. This creates a clear hierarchy of intrinsic safety based on fault tolerance. Right at the top, we have XI. This is the gold standard. The circuit remains perfectly safe even if two completely independent catastrophic component faults happen at the exact same time. Next down is XIB, which maintains its safety under a single component fault. And finally, we have XIC. This one guarantees the energy stays below ignition levels, but only during normal, fault-free operation. Section 4. Matching categories to zones. Let's take those categories and map them to specific hazardous environments in the real world. As you probably know, our operating environments are classified into zones based on how frequently explosive gas is actually present. Take Zone 0. This is an area where a gas hazard is continuous, like the dark, totally enclosed interior of a crude oil cargo tank. Because the risk there is just immense, the standards strictly demand XIA equipment. You absolutely must have that double fault tolerance. But then look at Zone 1. This is an area where gas is only likely to occur occasionally during normal operations, maybe a pump room. Here the standards give us a little more flexibility, so you're allowed to use either XIA or the single fault tolerant XIB. And finally, there's Zone 2. These are areas typically adjacent to Zone 1, maybe around relief valves, where a gas hazard is highly unlikely, and even if it does happen, it'll only stick around for a very short time. Since the ambient risk is so much lower, the standard permits the lowest tier of intrinsic safety, XI. In these zones, you'll actually also see XN, or non-sparking devices, quite often. The operating philosophy here is basically probability. The odds of your device experiencing a major fault at the exact same millisecond an unlikely gas leak occurs, well, it's statistically remote enough to be considered safe.
Section 5, Interactive Knowledge Check. Let's actively apply what we've just covered to a practical offshore scenario.
Okay, imagine you are designing a system for an offshore vessel. You've got a delicate sensor loop that needs to run directly inside a cargo tank interior. That is an environment completely saturated with flammable vapors, a classic Zone 0. Based on what we just went over, which intrinsic safety category is strictly required here? Take just a second to think through that risk-reward matrix.
All right, if you guessed XEA, you hit the nail right on the head. Because gas is continuously present inside that tank, the risk is constant. So the IEC standards step in and mandate the highest possible level of protection. XEI is literally the only category rated for Zone 0 environments, specifically because it maintains that critical energy limit even if two totally separate faults strike the circuit at the exact same time. So, to wrap this up, intrinsic safety completely flips the script by preventing ignition before it can even start. It uses barriers to aggressively clamp down voltage, current, and power, and it categorizes that protection into IA, IB, and IC, based on the fault tolerance you actually need. But that leaves us with a huge question. How do you actually prove that a complex loop of interconnected devices is mathematically safe? Can you really trust a simple formula to prevent a massive explosion? Well, in Part 2, we are going to dive into simple apparatus devices, which are so simple they barely need certification at all, and we'll break down the exact loop math you need to verify your system is truly safe. You absolutely won't want to miss it. Thanks for joining me for this explainer, and I'll catch you in the next one.